This is Mr. Beck Does Your Homework. This is AP Physics Homework 5.2, question 13. This problem ties together several major concepts. We have conservation of energy, we have three different types of energy, we have some work done by friction, and we have projectile motion. So what we see is here we have a spring with a spring constant, K. We have a distance the spring is compressed is 5.4 centimeters. We're going to have to watch out for that centimeters. We have a 476 gram object that is launched by that spring. Grams is going to have to be kilograms. We know that it goes over this area of friction with a friction coefficient of 0.2. It travels 1.5 meters there before it's launched off of the edge, winds up coming down, and a distance of 4.07 meters is how far it moves. We also know it falls 2.2 meters. So for this is a projectile motion question. So let's tackle that first because we're going to have to work all the way backwards to get to the spring constant. So the first thing we need to know is that it moves 4.07 meters. I'm just going to call that a distance of 4.07 meters. And we know it falls 2.2 meters in the y world. It falls 2.2 meters. Well, I know from my distance equals my initial velocity times time plus 1/2 of acceleration times time squared. I know that my initial velocity in the y direction is going to be 0, so this is going to go away, and I can rearrange this equation to get the time of flight is going to be the square root twice the height divided by the acceleration of gravity, square root of 2y over g. Now, that is the time it takes to fall this far, which is the same as the time it takes to fall over here. So that's the time I have, and this is the distance that it moved in the x world. So to get this speed, it's going to be this distance divided by that time. So I can simply write that my velocity v at that point is going to be the distance I have, d, divided by the time I just calculated right there as square root of 2y over g. So I've got a velocity that it leaves the table. Now that is the projectile motion part of this problem, because now I know the velocity that it leaves the table, and everything else here is going to be a conservation of energy problem and work changes energy. So it's going to have some kinetic energy here. It's going to have lost some kinetic energy because it's flying across this friction, and over here it's all spring energy. So since all of this is happening on the same level, I'm not even going to worry about this potential energy anymore. So what I'm going to do is I'm going to set my PE equal to 0 at this height. At this height, my PE equals 0. So I don't worry about potential energy anymore. So what I have is, at this point, I have some kinetic energy. Here, I've got some work done by friction. So that means that I had some kinetic energy initially over here. So I'll call this KE1 and KE2. Now this kinetic energy that it had at this point is going to be equal to the spring potential energy it had when the spring was compressed. So let me say that that is going to equal my PE spring right here is going to equal the kinetic energy there. So think through this again, conservation of energy wise. I have a spring potential energy that is released and becomes kinetic energy. That's got some kinetic energy. It hits this patch of friction, and negative work is done by friction, taking away some energy, and then I wind up with some kinetic energy right here. So now we start with this kinetic energy right here. I know that there, my kinetic energy is going to equal 1/2 the mass times the velocity squared. My mass is going to be my 476 grams, so that's going to be 0.476 kilograms. My velocity is going to be the velocity that I had right here. This velocity equals distance over time. So I know my mass, I know my velocity, I could figure out my kinetic energy at this point, so that is going to be kinetic energy 2. Now how much work is done by friction right here? How much is this kinetic energy over here less than this kinetic energy here? Well, that's the work done by friction. The work done by friction is going to be the force of friction times the distance that I traveled, force times distance. It's going to be negative because friction is acting opposite the direction that it's moving, but that's just going to be a quantity that I know it was taken away, so I'm going to add it back when I go back in time to figure out this kinetic energy. So the force of friction times the distance will give me the work done by friction. Well, the force of friction is mu times my normal force, and my normal force is going to be mg. So I get mu mgd is going to be the work done by friction. So that I can calculate mu mgd. Mu for me is 0.2, m is going to be 0.476, g is going to be 9.81, and the distance is going to be 1.5 meters. That is going to give me the work done by friction. Now, I have work done by friction that was taken away, resulting in this. So I know that my KE1 is going to equal my work plus my KE2. I'm adding it back to KE2 in order to go back in time to get KE1, because really it's KE minus work equals KE2. So if I add the work back, I have KE2 plus work giving me KE1. Now that KE1, I don't even have to calculate the velocity there, but that is the same as the potential energy that was stored in the spring. So the potential energy stored in the spring is 1/2 kx squared. That's how I'm going to figure out k. X in this case, for me, 5.4 centimeters, my x is going to be 0.054 meters is going to be my x. So you have to be careful with centimeters and meters. So square that, compare it to this kinetic energy, multiply by 2, divide by x squared, and that will leave me with the k that I'm looking for. Question 14 asks for this velocity. Well, we already figured that out, so that's easy because you already know the velocity that it leaves the table. Question 15 asks for the speed at which it hits the ground. So what we have to do there is just treat this section as a conservation of energy problem. So this velocity will relate to this kinetic energy that it had, but now what I have to do for that problem is say I have to include the potential energy that I ignored before. So now I've got my 1/2 mv squared, but I've also got some PE equals mgh. And that PE will be the amount of potential energy I have here, because that potential energy I'm going to lose as it falls down here, so there will be this much more kinetic energy. So I could even write that KE3 equals PE plus KE2. So when you've got your MGH here and the KE that you already know, add those two together. So here's this one, here's that one, and that'll give you a new kinetic energy equals 1/2 mv squared, and then you can find out your new speed total, because you'll have to have KE plus PE equals KE to get your speed at the bottom point.